is called hybridization. Hybridization. Okay. This chapter is very big. Huh? Hybridize. Okay. Generally, people, I write with S, British English, but people are using now American English. So you can write here Z. Hybridize. See, we had been in our day-to-day life, we had been always hearing the word hybrid. We had hybrid in the form of vegetables, flowers, and different things. That is, if you mix two things almost of the same family, then you get a new offspring which has inherited the properties of both, but individually it is different from them. Okay, so this is called hybridization. So we'll write the definition of hybridization. In chemistry, we say like that. The process of mixing atomic orbitals of nearly same energy to form a set of new orbitals of equivalent energies and shape is known as hybridization. Okay, please write.
So done.
So done.
Good. Then characteristics of hybridization. The number of hybridized orbital form is equal to J number of orbitals get hybrid. Please watch, don't write now. It's a very simple example, okay? Say you have made a cup of black tea, okay? Tea is there and sugar is there. By this time your sugar finished. Then that moment only you find one of your friend has come. So again you have made a cup of tea, but this tea does not have sugar. What to do? You cannot offer tea like this. And you also should not take like this. And what you will do? You will mix both of them. After mixing, when you pour back, you will find you have got again 2 cups of tea. But sweetness of the tea in both the cup is less than this and it is more than this. So the number of hybridized orbitals formed is equal to the number of orbitals get hybridized. It is we mix 2, we will get 2. Okay? So the energy and state will be same, just like the sweetness of the in both the cups of tea.
Sir, done.
Okay. Any orbital will not go for hybridization. Okay, there are some conditions are there. Like with anyone that we meet around us, would not go for making friends. There will be some conditions. Conditions for hybridization. Only the orbitals of nearly same energy belonging to some atom or ion can take part in hybridization. Second, it is the orbitals that undergo hybridization and not the electrons. Not the electrons. What is the meaning of this? Suppose you thought you want to rearrange the chairs in your drawing room. Okay. So in that case, you move the chair, but you don't move the person. After you arrange, the persons come and sit. Eh? Not the electrons. the electron cloud. In hybrid orbitals. You hybridized it, then electron has got. Hybrid orbitals repel each other. You have already, now you know the repulsion that you have already done VAC pair. Repel each other. And thus tend to be farthest apart. This is the same concept, we have got it from the VSPL. So until unless atoms do not combine with others, they never hybrid. Hybridization never occurs in isolated atom. Okay, we adjust ourselves when someone we meet. Otherwise, you don't adjust ourselves. It's isolated. But it takes place only at the time of bond formation. Then fifth, the shape of hybrid orbitals is like p orbital, means double shaped, except that two lobes are see, this is the p orbital now. Both of them are same, but in hybrid orbital you find one side is smaller, other side is bigger. Two lobes are unequal in size. Unequal in size. The larger lobe always has positive sign. What does it mean? Here electron density is more. Why? and bonding takes place to this. While smaller lobe has negative sign. Malfa देखी नहीं. We are going for example. Hybridization involving s, p, and d orbitals. Okay. So we know there are 3 p orbitals. Huh? So this is the shape of s orbital. Then see here we have 3 p orbitals. So it is z. This is z. This is x-axis. This is y. Y. See, this is px. This is py. And this is pz. Okay, so let me write here plus, minus. I can write it other ways. And what is the shape of d orbitals? We know. This is d orbitals. Huh? So this is s orbital. This is p orbitals. And this is d orbitals. Okay. So we'll take one by one. D orbitals are like this. This is, if this is plus, this is also plus. If this is minus, this is also minus.
So done.
Okay. Now we are going for S, P. Both are small letters. Huh? SP hybridization. Please remember, I have written here P. Means I have taken out of 3, I have taken 1. So we know only the orbitals with similar symmetry only undergoes hybridization. So this is S orbital. This Z, This is X. This is Y. Okay. So this is a bonding orbital. So in that case, you'll find we're taking only one. Okay, dear. So this is our, say it is Px. I know that Px. Huh? I write here Z. Only Z axis. I told you that when Z axis overlap, we get sigma bond, and for others we can get, okay, you can write because it is a S and P. You can write it. So you can write here X, X, Z, Z, Y, Y. So we are mixing both of them. When you mix both of them, then we are going to get a new set of orbitals. Okay. See here. But I'm very sorry. In your book, the way I'm drawing, that is the perfect one. But in your CBSE book, they have drawn in such a clear. So please excuse me. Because these theories I did not make. If your book they do not follow, because we are being told each hybridized orbital looks like p orbital, but one of the lobe is bigger and other is smaller. This is the theory. Okay, see here. This is one because I mix two, so I should get two. So in that case, and the hybridized orbital electron cloud they want to remain far away from each other. So this is plus for this orbit and minus for this same. And this is plus and this is minus. Okay. See here. So, my hand is not straight. Okay. So this is z-axis. Z-axis. This is x-axis. This is x-axis. This is y. See here. In this case, what has happened? In this case, after the formation, to avoid repulsion, they remain far away from each other. So in that case, what should be the bond angle between these two hybridized orbitals? See, it is 180 degree. So any molecule which is being formed by the sp hybridization, okay, this will be linear. So what is the structure here? The structure is linear, or also you call it cylindrical. Cylindrical. That is, it will look like this. See, this side on hybridized orbital is there, other is this side. So it looks like a cylinder. You will find they have written like this. This is one, and this is the other. But anyone will get confused with that. It looks like a p orbital only. They did not write a smaller loop. So please follow this. But in school you write like this. But this is the actual thing which I'm teaching. This is the actual hybridization. But in exam and school you please write. Okay. Because I have found many teachers they always write like this, as it is even in the book. Okay. We'll do example. See here. Beryllium atomic number is 4. So it is 1s2, 2s2. Okay? See, very interesting. First of all, the inner electrons never participate in bonding. It is only the outer electron take part in bonding. And we also know that completely filled orbitals, they are not supposed to form bond, because why? The electrons are already paired up. So they are not supposed to form bond. So in that case, but we know the beryllium valency is 2. And only unpaired electron can take part in bonding, but is already paired. Then why it should show a valency of 2? In that case, the valency of beryllium should have been 0. But why it is happening like this? Okay, the reason is that whenever beryllium comes in contact with some other molecule, they reorganize their electrons and they break the pair. After breaking the pair, they make it 2 unpaired electrons, and these 2 unpaired electrons combine with 2 different atoms. Okay. Now, I'm going to show you in a box diagram. How does this? Well, right now here, beryllium. Okay, and this is in the ground state. This is the ground state electronic configuration. For hybridization, you could require some energy. See. So, this is 1s. This is the pair of electrons. Then, this is 2s. This is the one. And see, I'm writing stepwise. In your book, they have given in same. I do not agree with the book. Okay, please don't think that Sir is talking so big. He is so proud, not like this. Because you have already learned from the atomic structure. Energies of all of them are different. If energies of all of them are different, then why should I write them in same line? Okay, now see. Is a very simple thing. If I want to have 2 unpaired electrons, what should I have to do? I have to break this pair and push off 1 electron here, because this is empty. All right. So in that case, you have to send it to other. It might have happened to many of you, because in childhood, suppose 2 of your sister or brothers or brother and sister, you sit in one room and study. And whenever you find a quarrel breaks up, then what will happen? Your mother or father will come and send you to 2 different rooms. All right? All right. So in this case, so in that case, to make unpair it, that is, I require the help of an empty orbital. So I'm going to send this electron from here to here. But again, we know that we have learned from atomic structure. If you simply pump an electron to the higher orbitals, that is called excited orbitals, excited state, it will again come back to its original ground state. So in that case, bonding is not going to last. So what should you do? You mix them together, just like we mixed 1 cup of tea with sugar and another cup of tea without sugar. When you mix them, the sugar from 1 cup did not migrate to the other cup. It remained there only. All right. So this is called hybridization. So now this is an hybridization you can do only at when you supply energy. So I'll call it now excitation. So what has happened now? See here. Inner orbital did not participate. I'll write like this. And out of these 3, Px, Py, and Pz, I have taken only 1. One of them I have taken. After taking 1, see, hybridized orbital, they have the same energy. Moment you mix them, the energy becomes same. then we know if if you have more than one orbitals of the same energy, then you have to fill up one by one. It is called Hund's rule of maximum multiplicity. So I have 2 electrons, one I'll put here and I'll put here. And these 2 I did not disturb. As I did not disturb, the energies and the shape does not change. So this is 1s, this is 2p, but what will be the name of this? The name of this will not be p, because it is now an altogether different orbitals. See, many of you are having biology. So in that process, suppose if I go for tissue culture, I take a red rose and I take a white rose. When I mix them, I do not know the technique. You are a biologist, you people may know better than me. Okay, when you mix them, the offspring that you get is pink. So you can't say pink is white, or you can't say pink is red, but it has inherited the property of both. So in that case, this one we call it SP. So this is the SP hybridized orbital. Okay. Now, what is the shape of SP? That I have already told you. SP is what? See, it is the beryllium. Okay, and this is the. So now I will not put plus here because I will show electron. And this is the electron we have. This. So this is the SP hybridization of beryllium. Now, what is the molecule that you have got? Beryllium chloride. Now these unpaired electrons, we know unpaired electrons are not stable. So now they are going to form bond with taking one electron from the chlorine. Halogen, electronic configuration of halogen, outermost shell electronic configuration of halogen is ns2np5. That is, s orbital is filled. One of the p orbitals have unpaired electron. So one of the unpaired electron of the p orbitals will now come, that half paired orbitals will come and overlap with this. All right. So what should I write now? Structure of beryllium chloride is Be. Okay. Now this is the chlorine. Chlorine use this p orbital to form a sigma bond. See, this is an always opposite spin overlaps. So this is the structure of beryllium chloride. If you don't understand, tell. Tell me. Again, I'm telling you, please hear. This is the electronic configuration of beryllium. Only the valence shell electron takes part in bonding. In case of beryllium, first of all we know that unpaired electrons takes part in bonding. But see here, this paired. So if you go by this theory, then this one should not form any bond. Why? See, take the example of helium. See, this is the electronic configuration of helium 1s2. Helium does not form any compound. Okay. Then why should it Why should it form? In that case, what do you find? Beryllium pushes one electron from its A to its valence shell p orbitals. But it should be a permanent affair. Because if you excite electron from atom, it goes to the higher energy level, and after that again it comes back. So we want a permanent solution. So what we do? We take out of the 3 orbitals, we take 1. Because all the orbitals have the same energy. You take 1. So after that we mix both of them. After mixing, we get a set of 2 hybridized orbitals, and all hybridized orbitals have the same energy. So according to the Hund's rule of maximum multiplicity, we have to put 1 more electron each. So we have put it. So now this is the shape of the hybridized orbital, because we are being told that hybridized orbitals have the same type of orbitals like p orbitals, but only one side is found to be bigger and another side is smaller. All right. So I have drawn it like this. But as I told you, in your textbook they did not draw the small lobes. So in your school, you don't draw the smaller lobes. All right. Now these unpaired electrons are now going to form bond with 2 chlorine atoms. So from chlorine atom, the unpaired electron belongs to the p orbital. So one chlorine has given its p orbital to overlap, other chlorine has given the p orbital to overlap from this. All right. So now they will ask you what is the bond angle and shape. See here, what is the bond angle here? The bond angle is 180 degrees. So you will write now here shape. What is the shape? Shape is linear, or you will write cylindrical. And bond angle? Bond angle is SP is always 180 degrees. সামনে না থাকলে সব বহুত মুশকিল। We'll draw another one. This is more important for your exam. Okay. We'll draw now C2H2. C2H2 that you know in school you have done. We call it acetylene, or his IPC name is ethyl. Okay. So now we'll go for carbon. Carbon is having configuration of 1s2, 2s2, and 2p2. So I'll make it a little more elaborate. 1s2, 2s2, you know the p orbitals have 3 subshells, and this is the one. 2px, 2py, 2. Okay. So now we have 2 electrons. So 2 electrons here will not be just like s orbital we have filled up. 2 orbitals I cannot put in px. Why? Because all 3 of them have the same energy. When 3 of them have the same energy, again I have to follow Hund's rule of maximum multiplicity. Okay. So I'll put 1 here and I'll put 1 here. So this is empty. All right. Now I have to go for hybridization. So what I'll do now here, I'll write here. This is 1. This is, see, all of us, we know the valency of carbon is 4. Okay. So all this I told you to remember. Now you'll understand why it is 4. See dear, this and this. We are being told, initially we are being told that valency E of an atom is the number of electrons in its outermost shell. That is the initial definition. But in that case, fluorine has in outermost shell 7 electrons. But in valency is not 7. Valency is 1 only. All right. So in that way, our definition is not correct. Initially, people did not have an idea. Later on, when they started understanding the valence chemical bonding, they have modified their definitions. Now, what does it say? That valency is nothing but the number of unpaired electrons the atom has in its valence shell. So, how many unpaired electrons it has? Carbon. Carbon has 2 unpaired electrons. So, if I say that valency of carbon is 2, then you will laugh, because little bit now you also know the sir is teaching all wrong thing. All right. So to make the valency of carbon 4, dear, if I remove this electron and send it here, then we'll have how many unpaired electrons? 1, 2, 3, and 4. All right. So the concept of the hybridization people initially started learned from carbon. Electronic configuration shows it has 2 unpaired electrons, but in all molecules, carbon show valency of 4. That is, when carbon forms the molecule with others, they change their electronic configuration. So now see, when I mix them, because in this case, if I send this electron here, what will happen? Don't write. Okay. Suppose I have taken only one of this orbit, and I have taken 2 px plus 2 px. Already 1 electron is here. So I have pushed this electron from here to here. See now, what will happen? Valency become 1. If I have taken py, 1 electron I shifted from here to here, I get this 2. Again, the valency become 1. So we find it is not possible. If I have to have 4 unpaired electron, there I have to take this unpaired electron 2pz. Okay, it is 2s plus 2p. See now this, and these 2 I did not disturb, so they're there. See here. How many unpaired electrons I have now? 1, 2, 3, 4. All right. So now I'll write down that. This is ground state before combination. Okay. When it goes for excited state, it is 1s. Then I mix this and this empty orbital. As I mix 2, I get 2. These 2 I did not mix. This, see here, these are hybridized. What should I call it? S. What should I call them? Because I did not mix. They have their own name. They will have their own shape. So this will be the hybridization, sp hybridization of carbon. Okay, now see, I'll go into drawing. Please remember, look, this, all 3 of them are perpendicular to each other. See here, these are the orbital I have drawn. So now, first I'll draw the hybridization. Okay. You have one electron here. This is the hybridized orbital. And these two I did not mix. So they'll have their own shape. See. See here. So it will have one electron here and one electron here. So this is the what is the angle here? Now what is the angle you have here? 180 degree. I'll write it now like this. 180. So this is the SP. শেষ আমি আমার শেষ হলে লই মুভি না লাগবে না আমি এটা কেটে নিচ্ছি সবই তো first we have made the hybridization of carbon, then after that I am going to draw it. Okay, so now this one though I cannot go very fast. See here, both the carbon is having sp hybridization. All right, see, this is our sp hybridization. Okay. Now see, please remember, sigma bonds are only formed by hybridized orbital. I'll write down later on. Now I have to draw this too. This. See here. Clear? Now, this is like this. See why I am drawing opposite? Simply because that only electron of opposite spin only the overlap. See. So I'm just showing it like this. Okay. So this is these are the hybridized orbital. These two. So they will come and overlap and form a sigma bond. Now see, these two are the unhybridized p orbitals 90 degree to the carbon. See here. So these two will overlap like this. These two from top and the front and back. And here other hybridized orbital, this will overlap on the top and the bottom. So this is pi bond. This is also pi bond. So in between two carbon atoms, in between two atoms, you will have only one sigma bond. And you can have one or two pi bonds. You cannot have three pi bonds between two atoms. So it is difficult for us to show. So we'll show it like this. Then this is overlap is going on. Okay, and this is overlap is going on. Now we have hydrogen. The hydrogen will bind to s orbital. Hydrogen will bind to s orbital. So this is the orbital diagram of acetyl. Okay, orbital diagram of acetylene. Suppose because molecule we can't see, bond also we cannot see by naked eye. Suppose you've got a divine sight. If you look, then you will find this is the way the bond is taking place. Okay, now what is the shape? Shape is here. I'll write it as linear or cylindrical. Why it is cylindrical? Okay. See, the sigma bond is inside this tube. And you have one pi bond here, another pi bond here. So you have an electron cloud from top and the bottom, and front and back. So if it looks like a cylinder, because of that we will write it cylindrical. And what is the bond angle? What is the HCC bond? Bond angle is 180 degrees. Orbital. So hybridized orbital from sigma bonds, and these are unhybridized p orbitals. They form the pi bonds. So what we will write now here? We'll write here note. Don't forget. Overlap overlapping on hybridized orbital by another hybridized orbital. See, this is one hybridized orbital, this is also another hybridized orbital. Okay? Or by another unhybridized orbital or sigma bonds. See, this is sigma bond, this is sigma bond. This is 1, 2. Pi bonds are formed by overlapping of unhybridized orbitals. See, it has 2 pi bond and pi bond. Please remember this and this and this is 1 pi bond. This and this is another pi bond, because it takes place on the top and the bottom. So don't confuse that there are 4 pi bonds. There are only 2 pi bonds are there. Third, the presence of triple bond. Triple bond. Why should I say triple bond? Because its structure is HC HC. See, the bond in the middle is sigma. Okay, so this is sigma. This is pi, and this is pi. Presence of triple bond between 2 atoms indicate that both the atoms have sp hybridization. Please remember, looking at the molecule itself, we'll be able to tell what type of hybridization it has. So now I'll do one more example for you. You should know. Okay, I told you the presence of triple bond between two atoms indicate that both the atoms have sp hybridization. See, now I go for third example. Say it is HCN. This is called hydrogen cyanide. It is very toxic gas. If you inhale it for a few minutes, it will lead to death of the person. Hydrogen cyanide. See here, you have carbon and nitrogen, both are having triple bond. So in that case, this is also sp. This is also this sp. We have already drawn. This one we did not. So I'll write now here for nitrogen. Okay, I'll do for carbon also. So I'll write like this. So what I'll take 2%. I've done 2% here. 1 and 1. So I'll write now here sp. I'll not write here s or p separately. These two I did not. So I'll write then 2px, 2py. Then I'll go for nitrogen. Nitrogen I know 1s2, 2s2, 2px1, 2py1, and 2pz1. Okay, so I'll take 2pz here. Because I told you it is the z orbital of p takes part in sigma bond, and the overlap of sigma bond gives us, overlap of the hybridized orbital gives us sigma bond, and between these three, among these three, middle one is sigma. So I'll write now here. Ground state is 1s, 2s, okay, 2px, 2py, and 1, 2, 3. All right. So I'm going to mix this with this. So See now, 2. How many orbitals I'm going to get? This and this I'm mixing. I'll get 2. How many electrons I have now here? 2 plus 1, 3. So it is going to follow Hund's rule. So 1, 2. Then it will come here. 3. So this one I did not mix. 2px, 2p1. Okay. Now I'm going to draw this hybridized orbital here. See here. One you have here, one you have. These are the unhybridized orbital. Okay. And this for nitrogen, see here nicely. See, this is the reason for which you have to put smaller orbitals here. Then only you know these two are hybridized orbital, these two are unhybridized orbital. Now see here. Here you have a pair of electron and you have unpaired electron. All right? So I'll write it like this and this. See, this pair of electron will not form bond because it is already paired. This is going to form bond. Okay? So I'm going to draw both side by side. Here you have 1 and here you have 1. This. Now nitrogen, this will overlap with this. See, this you have a pair of electrons. See. This. And this is going to form bond with hydrogen. So this is the orbital diagram of nitrogen. What is the shape? Linear or cylindrical? What is the angle? Bond angle? See here, HCN bond angle is 180 degrees. Yeah, do some change here. This is this for nitrogen. Okay, done. You have class at what? 9 o'clock?
Yes, sir.
Acha. Dear, I want to tell you one thing. This Wednesday again I have to go out in the morning. So I have already missed 2 classes. So I think I will take some extra class to compensate. So said this Friday, Wednesday will not have any class in the morning. All right.
Yes, sir.
শাদি থাকলে জন্য খেতে ভালো লাগে রান্না সব জিনিস কি সিদ্ধ করে রান্না করে করে অবশ্য সংগ্রহ করে ভালো লাগে করবো